Hello friends, myself Venugopal Panchmarthi, working as a senior curriculum engineer at Masai. In this video, we are going to talk about different sorting algorithms. Okay, yeah. So friends, we have there are many sorting algorithms. So among that, we have 5 popular sorting algorithms are there. So those are bubble sort, selection sort, insertion sort, then merge sort, quick sort, and we have few more algorithms like heap sort, radix sort, counting sort. Those also there. Okay, but for the time being, we are going to discuss first 5. In this first 5 also, I'll talk about first 3 sorting algorithms. If time permits, then we'll take about 4 and 5 also, or else we'll take it in a separate class. Okay, right. Now first so here I mean to say discussing about all these algorithms means, so first I'll talk about what is meant by this bubble sort, and I'll take some examples. So with that examples, I'll do some kind of analysis, right? Then we will write a code. After writing the code, we will do the what is exactly the time and space complexity also. So please pay attention to each and every part of that video. Okay, good. Now first let's talk about the bubble sort. Okay, so the input to this bubble sort is a random generated array. So this input can be of some random integers. So here n is equal to 6 elements. So I have taken one array which is out of 6 factorial permutations. So one permutation I have taken here. Now output will be all the elements. You should put it in the non-decreasing order, which means all elements should be in the increasing order. If duplicates are there, then sometimes maybe repeated also possible. So here, just for the simplicity, I have taken all distinct elements, right? Okay, cool. Now first I'll explain what is the idea behind the bubble sort, and then I'll show some. With this example, I will try to find out how we will get the final sorted array. Then based on how we have done, we will try to write the code also. Okay, so the idea is, basically the bubble sort works by repeatedly swapping the adjacent elements if they are not in the proper order. Okay, so here 2 things you should know. One is what is meant by repeatedly swapping the adjacent elements, and what is meant by not in the proper order, right? So if you take elements like this 9, 2, 4, first to compare adjacent 2 elements, you try to compare friends. Now you see 9, 2. Now our agenda is, our objective is to sort elements in the increasing order. Okay, so which means something like 2, 4, 9. Now when you compare these two, now this is the final order, which means first 2 has to come, after that 9 has to come, may not be immediately. Now see 9, 2, they are not in the proper order. So when they are not in the proper order, you should put. So how you are going to put in the proper order, like 2, 9? Simple, you need to swap these 2. So in this example, these 2 points are covered. So this thing repeatedly should supposed to happen till the array getting sorted. Okay, right. Now you take this example. So let me take the original input array which they have given. This is right. Okay, so let me take this input array. Now this actually bubble sort will works based on the passes, friends. Okay, so you should know what is meant by passes. Okay, right. So I'll explain in first pass what will happen. So I'll write it P1, which corresponding to the first pass. So P1 corresponding to the first pass. Okay, now these 2 elements are being compared. Now let me check, are they in the proper order? No. So the proper order means 7, 9. This is the proper order, but now 9, 7 are not proper order. So let me swap them. So if I swap these 2, so 7 will be coming and 9 will be like this. So I simply swap. Remember, adjacent elements only you need to swap. That is the idea of the bubble sort. Okay, and the remaining elements will stay as it is. So that is 6, 4, 2, 1. So in the first pass, this is the first step. Now what is the next step? So the next step will be, now, okay, so we have compared these 2 elements, right? Which means these 2 elements we have compared, right? And they are getting swapped. Now in the next step, you need to compare these 2 elements. Okay, now are they in the proper order? No, they are not in the proper order. So when they are not in the proper order, you need to swap. So which means this will be 6 and this will be 9, and the remaining elements will stay as it is. Okay, so in the next time what will happen? So let me take this again. Now you need to swap. See, every time 2 adjacent elements. Okay, so these 2 you have compared. So next time you have to compare. Wait, I think Yes. So next you need to compare these two. So when you compare these two, are they in the proper order? No. Then you need to swap these two. So which means this will be 4 and this will be 9. Okay. Now, so this pass will continue till the end of the array. Okay. Now next you need to compare these two elements. Okay. Are they in the proper order? No, they are not in the proper order, which means you need to swap these two. So which means, so 2 will be coming here and 9 will be going here. Again, you need to swap again. Okay, so let me take this. Now try to compare these two elements. Are they in the proper order? No. Then again swap. So which means then this will be 1 and this will be 9. Next, is there anything to compare here? No, right? Therefore, first pass will be ended up here. Okay, now pass 1 is completed. Now this is the input for the pass to pass 1 actually. So this is the input of the first pass, that is P1. Now what is the output that you got at the end of the pass? This one. So this is the output that you got at the end of the P1. Okay. Now at the end of the first pass, what happened here? So every two existence elements we have compared. If they are not in the proper order, we have swapped, right? Okay. This is the output that you got. Now this output, whatever the output that you got after P1, will be supplied as input to the next pass. Okay. See how long these passes will be continue, as long as your array is sorted. Okay. Now let me take this and this I'll supply as input to the second pass. So which means maybe I'll take these to next slide. Okay, that I'll put it here. Okay, now actually this is the input of the P2 friends, which means our next pass will be started from here. So let me write P2. This is P2. So again same thing will repeat. That is, you are going to compare first two elements. Okay, are they in the proper order? No, they are not in the proper order. So which means, just for our understanding purpose, every time I'll be rewriting. Okay, let me write it here. If these two are not in the proper order, so we need to swap these two. So which means, so 6 and this is 7. Okay, let me use a different color. So you need to swap these two. So 6 will be coming and 7 will be going here. And the remaining elements will as it is. Okay, next time you need to compare these two elements. So next, you need to compare these two elements. Okay. Are they in the proper order? No, they are not in the proper order. So which means again a swap will be happening. So here you need to swap these two. So when you swap these two, simple. So 4 will be coming here. So 4 will be coming here and 7 will be coming here. So next time you need to compare these two. How long this should happen? Till the end of the array. Which means right now you are in the second pass and this should continue till the end of the array. Okay. So let me copy this. Now you are compared these two now, so they are not in the proper order, so you need to swap. So 2 will be coming here and 7 will be going here. And next time what will happen? Again you have to compare these two. So when you compare, again they are not in the proper order, so therefore a swap will happen. So one more swap will happen, right? Okay. So okay, so let's read this. So if you compare these two, not in proper order again, so swap will happen, which means 1 will be coming here and 7 will be going here. Okay. Now next time you have to compare these two elements. These two elements you need to compare. But you already know that at the end of the first pass, one element came here, friends. Okay, just to remember what is the specialty of this element, that I'll talk in some time. In the end of the second pass, you just to try to check these two, they are in the proper order. Just remember, at the end of the second pass, you have compared with this element and you got these two are in the proper order. So they are in the proper order. Just remember, so when we implement the code now, this point will be helpful. Okay. Now, actually, this is the input which you have given. This is the input of the P2, which means second pass input that you have given. What is second pass input? That is output of the P1. Output of the P1 you given as input of P2. Okay, so since you given something as input to the P2, then definitely something you will get output, right? Yes. So this is output of P2. So that is output of P2. Okay. Now this will be supplied as into the next pass, that is P3. Like how long these passes will be going on? Simple. As long as array is sorted, this thing will happen. Now let me take this array, which is output of the P2. This I'll take it to the next slide and I'll talk about the P3, what will happen. Okay, just see this. Now I'll be taking this array, which is output of the P2, and this I'll take to the next slide and I'll explain what will happen in the next pass. Okay, so 2, 7, 9. I think these elements are 6, 4, 2, 1, 7, 9. 6, 4, 6, 4, 2, 1, 7, 9. 7, 9. Okay. Now let me talk about P3, friends. So third pass, how it will happen. Again, you have to start from the beginning only, no other way. Okay. So now if I start from here, so again I'm going to compare these two. So I'm going to compare these two elements. So are they in the proper order? No, they are not in the proper order. So I'll copy. Okay. So you need to swap these two first two elements. So which means 4 will be coming 6. Again, compare these two. So let me write it here. When you are comparing these two, again they are not in the proper order. So which means you need to swap. So when you swap these two, so this is 2. So this is 2. So we have to swap these two now. Then so 6, 2 will be coming and 6 will be coming here. Okay. So again you have to compare these two. Again not in the proper order. So obviously you need to swap. So you need to swap these two, which means so 1, 6. 1, 6. Now again, when you have to compare these two, are they in the proper order? Yes. Okay. Then if they are in proper order, swap is not required. Okay. Again, next pass. So let me take, because no changes happen. These two you have compared, so swap is not required. Again, when you try to compare, so again they are in the proper order, swap is not required. So this is actually the input of P3, friends. So this is input of P3, which means third pass, this is the input you have given. What is the output that you have got? This is the output that you have got at the end of the P3. Now this P3 will be supplied as input to the next part, that is P4. Like how long this passes? As I said earlier, this will happen as this array is sorted. Okay, so let me quickly talk about P4 also. Okay, so this I'll take, add it to the next slide. See, don't worry, whatever I am writing here, this I'll give to you, so you can use this soft copy as a notes. Okay. So at then I'll in the comment section wherever, so I'll add this notes in the description, friends. Now this is 4, 2, 1, 6, 7, 9. Okay, so 6, 7, 9. So this is basically output of the P3. Now this will be given as what? Input to the P4, because next pass will continue. So this is actually input to the P4. So now again I'll start the P4. Okay, now same story, friends. So you have to compare these two elements again. So compare these two. Story always, every pass will start from the first two elements only. Now when I compare these two, again they are not in the proper order. So you simply copy them. Okay, and you have to swap. Now if I swap these two, so 2 will be coming and 4 will be coming here. Again, compare these two. They are not in the proper order. So you need to swap. So you need to swap, which means 1, 4. So this is 1 and this will be 4. Okay. Now again, when you compare these two, they are in the proper order, friends. So swap is not required. Similarly, when you compare these two, okay, they are in the proper order. So swap is not required. Again, when you compare, they are in the proper order. So swap is not required. Okay, so actually I'm not writing explicitly, but you can see this. So here also with element 4, these all not required to compare. This is at the P4. Right? So this is the output that you have got at the end of the P4. So this is the output that you have got at the end of the P4. Now this will be supplied as input to the next part, that is P5. So let me take this and I'll take to the next slide. This will be input of P5. So which is nothing but 2, 1, 4. So 2, 1, 4, 6, I think 7, 9. 6, 7, 9. 6, 7, 9. Okay. Now this is what, friends? Output of the P4. Na? So which will be act as input of the P5. So this will be act as input of P5. So input to the next pass, that is P5. P5. Okay. See why I'm explaining each and every case now, because this will help you to write a code on your own way. That is the reason I'm talking in depth. Okay. Now P5, again the story will start from the first two elements. So story will start from the first two elements. Okay, again now see 2, 1, again they are not in the proper order. Therefore no other option. You need to swap these two. Right? So which is 1 and which is 2. Okay. Next, see this is what P5 going on, friends. So currently pass 5 is going on. Okay. And now again, so these two compared, yes, swap is happened. Next, proper order. So proper order. Again, they are in the proper order. So again, they are in the proper order. Okay. So no further not required. Next P6, only one element will be left out, friends. So it is wrong. So we have observed that at the end of the P5, so only one element is left and all other elements are sorted. So you can stop the process here itself. Which means if n is equal to 6, only 5 passes are enough. Only 5 passes are enough. N minus 1 passes. Now, what I will do, I will try to take what of the output that I have got at the end of the every pass, and you can observe some points here. Some beautiful points you can observe here. Okay, let me take one by one. Okay, so this is the original sorted array, original input array. Na? So this I will take to the next fresh slide. So, yeah. So, okay. This is the original input array, friends. So original input array, you can also call it as input of the P1, which means first pass you can call. Next, second pass output, I'll see what is the output of the P1. Okay. So this is the output that you have got at the end of the P1. So which is slide? This slide, let me add one by one. So output of the P1 and P2 output also I'll take. Yes, this is the output of the P2. Output of the P2. Okay, so this is output of the P2. Next, output of P3, let me take. Yes, this is the output of the P3. Because see, why I'm showing this now, so you'll get to know in some time. So this is output of P3, then output of P4. So let me take output of P4 also. Output of P4. Then finally, this is output of P5. Okay, this is output of P5. So these are the 5 outputs we have run, because 5 passes we have run. So this is output of P1. So this is, let me write it here. So this is P1 output, and this is P2 output, and this is P3 output. This is P4 output. Similarly, this is P5 output. Okay. Now, see here, friend, just if you observe carefully, at the end of the P1, first largest element in the array coming to its final position, friends. Because in the sorted array, obviously, the maximum element will go at the end. Assume we are sorting in the increasing order. Next step, if you see, second maximum will be coming here at the end of the P2. At the end of the P3, third maximum is coming here. At the end of the P4, fourth maximum is coming here. At the end of the P5, fifth maximum is coming here. If total 6 elements are there, obviously leftover part is the 6th maximum. Correct? So that's why I told not last pass is not required. So you see the beauty, right? So when you put some stone in a water, so it will bubbles like till the end. Right? Maybe you can have some water in a bowl or in a bucket. You put a stone inside that, so it will bubble and go till the end. Right? So you take a bucket of water and you put a stone inside the center. It will go bubble. Similarly, here also you see how the elements is bubbling up. So first element going first maximum, second element next, third element, fourth element, fifth element. Like that, it's going in a bubble. So that's why this name itself given as a bubble sort. I hope you got the idea, na? So it runs on a passes. At first pass, what is happening? First maximum going at the end. Second pass, second maximum going at second from the ending. Like the third pass, fourth pass, fifth pass. If n is equal, if in general n elements are there, okay, then n minus passes are enough. Okay, right. Now let me try to implement this code. So let me try to implement this code. Where it is? I think initially. So I'll take this. I hope now you got the idea, na, what is happening. So let me go here. So here itself I'll put, and let's see its implementation, friends. Okay. Now 2 things we have seen here. Every time passes are happening, in one pass, some story is happening. See, in the first pass, some iterations are happening, and what you are doing every pass, two adjacent elements you are comparing. So next pass also same thing happening. Third pass also same thing. Fourth pass also same thing, which means you require two loops here. One loop is for passes, another loop is for what happening inside the passes. So two loops are required. Okay, let me take one for loop, which is just for passes only. Okay, I'll write it here. So for int I is equal to 0. Okay, I less than n minus 1, I plus plus. Oh, as I told, n minus one passes are enough. Okay, let me go inside. Now see this, friends. For int j is equal to 0. Okay, now okay, j is equal to 0. J less than, I don't know, friends, what I need to write. Some I leave like that. J plus plus, j plus plus, and see inside what you have to write. So let me go to the first pass. Let me go to the first pass where p1 is equal to here. Okay, I is equal to 0. So I is equal to 0, which means in the first pass, see what is happening. So what you are comparing? You are comparing adjacent to two elements, right? So let me take one more variable j. So let me take one more variable j, because irrespective of the passes, always story start from the beginning. So every time inner loop you should start from the beginning only. 0 to how long I should run at this point of time, I don't know. Okay, let me derive this. Okay, so you are comparing array of j value is bigger than array of j plus 1, which means they are not in the proper order, obviously, right? Because this element is bigger compared to this, then you need to put this one here, this one here. So obviously you have to swap. Now check here. Initially I also equal to 0. Throughout this pass I will be at 0 only. Next pass I will become 1. Though in the next pass I becomes 1, you need to start j from the beginning only. That is what we have seen here. So j value you start from here. Okay, now compare these two. If this is bigger, then what you have done, we have swapped them. Next time j value goes here, which means here. Again, if this is bigger than this, greater, we have swapped that, right? Okay, so we'll keep same thing here. And remember, we haven't finished this. If okay, array of j value, okay, is greater, compared to array of j plus 1, so you just need to swap these two. Okay, so how you will swap? By taking the third variable you can swap. Even using two variables also you can swap. This time being, let me take temp array of j, and array of j is equal to array of j plus 1, then array of j plus 1 is equal to temp. So this is how we will swap, right? This is how we'll swap. Okay, this for loop is over. Now if you try to fill that condition, second loop condition, then story will be over. Okay, now let's go back to the passes previously and we will see what is happening. Okay, now see here, friends, when I is equal to 0, which means in the first pass where you will start the j value and where you have ended, we will check. So you have started j value at the 0. Okay, and where till how long we have done in p1. Okay, here when j is equal to 4, we have compared these two, but after that there is nothing to compare. If you try to compare array of 5 and array of 6, you will get in Java array index out of bound exception, or maybe in JavaScript you might get an undefined behavior, because you have array only till 5, 5th index, 6th index no element is there. So j we have run till 4th element. So let me write it here. So j value we have run 0 to 4. Okay, so this I will put it here. Next, see, when I becomes 1, what happened, we will check. When I becomes 1, again let me go to the second pass. So when j is equal to, okay, so till j is equal to 0, okay, 1 also okay, 2 also okay, j is equal to 3 also okay, but j is equal to 4, okay, not required to compare, friends. That is what I have told. If you remember here, I have told, please remember one point, 9 came here, then these two I told not necessary to compare. Why not necessary? Because we already know first maximum came to at the end. If this is the maximum, then definitely whatever elements you take on its left side will definitely smaller than 9. Then only 9 will become the first maximum, right? So this comparison not required. So therefore j value, if you run till 3, that is enough in the second pass. So which means in the P2, okay, in the P2, j is equal to 0, okay, to 3, it is enough. That is what we have seen, friends. Next, we can see one more I value. So usually you can put this this condition here. Now next, I is equal to 2. Let's see what will happen. So irrespective of the I value, j will always start from the 0th index. Okay. Let's go to the P3. Where is P3? Yes. Now when P3, okay, J0, yes, J is equal to 1, no problem. J is equal to 2, also no problem. And when you see J is equal to 3, okay, already 2 elements came to its correct position. Because how P3 is coming? From P2 only. From P2, we already know second maximum will come here. Right? Okay. Now is it required, friends? Comparing these comparison is required. You know already this is the second maximum. Any element you take, if duplicates are there, then 7 can be present, or else all these elements will be less than 7. So which means this is not required. So you can run j till 2. That is enough. So j is equal to 2. That is enough. 0 to 2. Like that you can continue. Okay. Now if n is equal to 6, see here, because n is already given array length. If n is equal to 6, I is equal to 0, how long I will be going here? 4. Using 6 comma 0, how will I get value? 4. Using 6 comma 1, how will I get value? 3. Using 6 comma 2, how will I get value? 2. If you try to find out that condition, then easily you can put it up here. Now see here, simple. 6 minus 0, what can I do this? 6 minus 0, which is 6. I have to get value 4. So can I do minus 2? Yes. You will get 4. Similarly, how did I get this 3? Simple. See, because I is playing a role here. I means every pass, correct now? Because of passes only where this j value is behaving, right? Now this 6 minus 1, okay, minus 1. Minus 2, okay. 6 minus 1, 4. Okay, 6 minus 1, 5. 5 minus 2, 3. Similarly, here also you see, which means I am trying to find out this ending index of the j, friends. So 6 minus 2 minus 2. Okay, so which means you can clearly see this is n minus I minus 2, which is inclusive, friends, less than or equal to. If you don't want to write equal to symbol, you can simply write less than n minus I minus 1. Okay, both are fine. So therefore, it is easy, right? Now, since if you know this concept, then only you can write this. Otherwise, many people will by heart these two. I less than n minus 1, j less than n minus I minus 1. But why? This is the answer. Okay. So, n minus I minus 1. Now, we have completed the bubble sort code. We have completed the code of the bubble sort. Okay. Next, what is pending? Obviously, analysis. Now, let's analyze, friends. So, same thing I have kept here. Okay. Now, let's analyze, friends. Okay, time and space complexity analysis. Now let me take the code as it is here. Okay, so generally any program you take, so time complexity, space complexity, so depends on the what type of input that you are passing. So let's forget about space, concentrate on the time. What kind of input that you are passing to this program, based on the time complexity will vary. Okay, two types of inputs that I want to concentrate here. One is best case input and worst case input. So one is best case input, second is worst case input, so in between average case is also there. So which, if you want to find out the average case, now you require some probabilistic analysis, but let's ignore, for concentrate on only on the best case and worst case. Okay, so what is meant by best case input? For any program, okay, it should take the minimum amount of time. Then that type of input you are going to call it as the best case input. Okay, many people have some confusions here. So the best case input means a program which you are passing the input in such a way that it should take the minimal amount of time, irrespective of input, irrespective of size of the input, whatever it is. Okay, your algorithm should take minimal amount of time. Okay, so here our problem is to sort an element, right? You want to sort all the elements in the increasing order. Now you pass all elements already in the increasing order. Then sorting is required there? No, no. So let me take two types of input, friends. So one is I'll take best case input. Second, I'll take worst case input. Okay. Let me take one input here. Okay. So let me take one empty array. Okay, so this is empty array I have taken. First I want to concentrate on the best case. So if all elements are sorted, maybe 10, 20, 30, 40, 50, 60. Okay, let me take one input where all elements are sorted. Okay, now here the time complexity depends upon two things here. One is comparisons and swapping. So we need to see how many comparisons are happening and how many swappings are happening. Based on that, the time complexity will depends. So two things. One is how many, this is comparison. So this is swapping. How many swap operations? How many comparisons? Because this is comparison sort, right? Now, first time, when I is equal to 0, let's analyze one by pass by pass, what is happening. I is equal to 0, I is equal to 0. Now, J value will start from 0. So, J value will start from 0. Okay. Now, here one comparison is happened. Is 10 is greater than 20? Is this condition is true? Yes, this condition is true. No, this condition is false. Then swap will not happen. So, let me put a variable just to count how many comparisons are happening. So, initially one comparison is happened and swap is not happened. Okay, next. J value will goes here. 20, 30. Yes, you have comparison. Comparisons are happened, but swap is not happened because this condition false now. Next, these two elements, comparison is happened, but swap is not happened. Next to these two elements, comparison is happened, but swap is not happened. Why swap is not happened? Because they are in the increasing order. So swap is not required. Next, comparison is happening, but swap is not happening. Okay, for the first time, J value starting from 0, it went till the last but one. Okay, so we have identified 5 comparisons were happened and 0 swaps. 5 comparisons plus 0 swaps. Okay, next. Just remember this 5 comparisons. Next, I value will becomes 1. Okay, so just see this. So at the end, just to remember, friends, just remember this. So far we have happened 5 comparisons. Okay, just remember, and 0 swap. So 5 comparisons plus 0 swaps. 0 swaps. Next, when I becomes 1, I becomes 1. So J value will start at where? 0. And to how long it will go? How long it will go? N minus I minus 1, which means 6 minus 1 minus 1 till 5th. Which means 0 to 4 it will go. 0 to 4 it will go. Earlier this is 0 to 5. 0 to 5. Next, here also try to count how many comparisons are happened. Okay, when I is equal to 1, again J should start from 0. So 1 comparison, 2 comparison, 3 comparison, 4 comparisons. Okay, when I here, comparison will not happen. Because first pass we already know last element will come, first maximum will come at the ending, then there is no use of even comparing these two also. So 4 comparisons will happen. 4 comparisons plus 0 swaps. 0 swaps. So like that, if you go, when n is equal to 6, what will happen is, so I'm not writing remaining different, second pass, third pass and all. Only 2 passes we have done, third, fourth pass I'm not writing. So if you see 0 swaps are happen. And what about comparisons? Because time will depends upon 2 things, comparisons as well as swappings. So no swaps are happened, but comparisons are happened now. So which is 5 plus 4 plus 3 plus 2 plus 1. So if n is equal to 6, it is 5 plus 4 plus 3 plus 2 plus 1. In general, we can identify some pattern here. So in general, this is n minus 1 plus n minus 2 plus and so on plus 1. So which is nothing but sum of the first n minus 1 natural numbers. We know sum of the first n natural numbers are n into n plus 1 by 2. But we have n minus 1, which is n into n minus 1 by 2. Simple. In place of n, you substitute n minus 1 because we have only n minus 1 elements. So n into n minus 1 by 2. So this is nothing but order of n square. Because highest nth degree term n squared, so order of n squared. So the best case input here, our time complexity will be order of n squared. Okay, right. Now let me talk about worst case input also. Worst case input means for the input which your algorithm is taking largest amount of time. It is doing maximum amount of work. So here only comparison, no swap. Let me take another input where comparison will happen along with swaps also. Here no swap. let me take, okay, maybe I'll take this, go to the next slide, and okay, let me take a different input. Okay, so where swaps also will happen. Maybe I'll take all elements in the reverse order. So let me take 60, then 50, then 40. Okay, so 30, then 20, and then 10. So number of elements are equal to 6, right? Now again, same story. So start I is equal to 0. You start I is equal to 0. Okay. Now j value, this will start from 0 and 2. Okay. 5 it will go. 0 to 5. Okay. First you compare these two. Yes. Your comparison will happen. Along with swap also will happen. So here, how many comparisons you are do? Those many swaps will happen here. Yes, comparison. Okay. Because these elements in the not in the proper order. So you need to swap. So if I swap, what will happen? I'll write it here itself. So that is 50 and this is 60. Okay. Now again compare these two. When you compare these two, again not in the proper order. So you need to swap, which means 40 will be here and 60 will be here. Again you compare these two, not in the proper order. So swap. So I'm writing here itself in everything single cell only. So 60. Again comparison will happen. So which means so 20, then 60. Again comparison will happen and along with swap also will happen, which means 10 will be coming, 60 will be here. So here comparisons also n into n minus 1 by 2. So comparison plus swaps now. Time complexity depends upon. Okay. So comparisons are n into n minus 1 by 2 and swaps also n into n minus 1 by 2. Worst case. Okay. So overall n square comparisons, I mean in terms of order and order of n square swaps. So overall n square, 2n square, 2 you can take it out. Here also time complexity is big O of n square. Big O of n square. Now worst case input also it is giving order of n square. Then best case input also it is giving order of n square time complexity. So can you do some changes in such a way that will you reduce time best case input time complexity? Yes, we can do, friends. See, in the first iteration, okay, if no swaps are happened, then what does it mean? Just think and tell me. By the end of the first iteration, okay, first pass, if no swap is happened, then what does it mean? Array is sorted, right? So if array is sorted, then what is the requirement of swaps? Getting now? So therefore, one beautiful thing we can write inside this. Okay, that is inside the first for loop, where I'm entering into the first pass. Okay, I'll take one variable here, friends. Let me take one flag variable. Let me take this is of a boolean type. So flag is equal to, initially I'll take false. Okay, where boolean type it can take either true or false. Okay, at the end of the first for loop, okay, if there is a swap happening, which means swap happening means what? Control will enter inside that if block, which means this if condition will become true and the control will enter inside, which means this swap will happen. Then I will write here swap is equal to true, which means yes, swap is happened. Okay, once if this swap is happened, it will come out of this for loop. Here I will check if flag is equal to, still it is false, which means what is meant by at the end of this for loop, if flag is still false only, then what does it mean? It is not enter inside this if block. Then what does it mean? Swap is not happened, which means this condition is false. So if flag is false, then what is the purpose of continuing the remaining passes? Right? In the first pass itself, you came to know that the array is in sorted order. Then further passes you please skip it, not required. So that the next comparisons we are basically ignoring. Then you can write break, so that this for loop will break. So then what we can do, friends, after n minus 1, whatever the passes are there now, these comparisons, this we can remove, not required, which means only this will come in the time complexity. Then it will become order of n as the time complexity. That is the beauty here. That is the beauty. Order of n is the time complexity. So best case time complexity bubble sort is order of n. Okay. By adding this flag, does it improve anything to the worst case? Improve means, does it reduce the worst case time complexity? No. So worst case input, always this if condition will become true and this swap will happen. This condition will never be true. Okay. So worst case, we can't reduce, friends. So its time is order of n square. Its time is order of n square. Okay. So that is the complete idea of the bubble sort. Right. complete analysis. Order of n, best case time complexity, order of n square, worst case time complexity, right? So this is the story of the bubble solutions. Okay, I think we have covered all. Now we have given one interesting problem here. So just read this question. Maybe you can pause the video and you try to think yourself and you can come up with the solution. Okay, please pause the video and work out. Okay, now I assume that you have already tried this question. Now let me start explaining this question. Okay, so what this problem they are saying, an array contain 4 occurrences of zeros. Okay, see this, an array contain 4 occurrence of zeros. Okay, then 5 occurrence of 1. Okay, and 3 occurrence of 2 in any order, which means they can come in the any order. The array is to be sorted using swap operations. Okay, using swap operations only array needs to be sorted, and elements that are swapped need to be adjacent. So from this what we can conclude? From this, if array adjacent elements are being swapped, means we can conclude this can be done using bubble sort, right? We have already seen bubble sort. Okay, now 2 questions are there, A comma B. What is the minimum number of swaps need to sort such that in the worst case? So in the worst case, if swaps has to happen means, then what kind of array should I supposed to take? From the previous slide itself, we got a conclusion that if array is in the decreasing order, then more swaps will happen. Correct, no? So they told any order. Let me take a 1 order where all elements are in the decreasing order I will take. So if I take all elements in the decreasing order, so total 3 occurrences of 2s are there. So 2, 2, 2. Then 5 occurrences of 1s are there, which means 1, 1, 1, 1, 1. Then 4 occurrences of zeros are there. 0, 0, 0, 0. Okay. Now you need to count how many swaps that will happen. See, please don't get confused. They are asking minimum number of swaps. Okay. In worst case, okay, in worst case, how many minimum swaps will happen? It doesn't mean that you take sorted array and 0 swaps. No. Worst case, how many swaps that will happen? Yes, when worst case will happen, if array input is like this. Like this, now try to find out how many swaps. Okay, see, actually when swap will happen, friends, when they are not in the proper order. Again, try to run in the different passes. So let me see what will happen in the first pass. P1. So in the first pass, what will happen? First pass, it will go on the multiple iterations, right? Okay. Now, first I'll take these 2. They are in the proper order? No. Proper order? Yeah, they are in proper order. And now try to see these 2. Now see here, they are not in the proper order. Here, they are not in the proper order, friends. Then what will happen? Here, one swap will happen. So, which means 1 will come in here and 2 will go here. Again, they are not in the proper order. So, 1 more swap. So, let me take one variable called swap. Initially, I'll set it to 0. I'll try to increment it. Whenever swap, I'll try to increment this. Okay. So, this is 2, 2. This also 2, 3 2s and this one. Okay. So, with adjacents these 2. So, no problem. No problem. Here it is a problem. Okay, 2, 1, yes, swap will happen. So I'll increment swap to 1. Then which means this will be 1 and this will be 2. Okay. Now again, now if you check, like, just simply see, friends. I mean, you in fact to solve this problem, no need to do complete question also. See how many elements that are there which are less than 2. Definitely with those all these elements, this swap will happen. Are you all agree with me? Yes. This 2, you take any element that is present. If it is less than 2, then definitely those all elements will create not proper order with this 2. So if you want to make them as a proper order, then what you should do? You should obviously swap them. So therefore, with the 2, now already one swap is happened here. With this 2, try to see how many elements that are which strictly less than 2. Those many swaps will happen. Correct, no? So then finally it will become 9. Now, because already 1 and total, if you see 8 elements will present. 1, 2, 3, 4, 5, 6, 7, 8 elements are there. So at the end of the P1, how the story will looks like? At the end of the P1, how the story looks like? So here 2, 2, here you will be getting 1. Here you will be getting 1 here. Similarly, here also you will be getting 1. Here also you will be getting 1. The first maximum will go till the end, which means somewhere here at the end 2 will goes. That is what we can 100% sure. And the remaining elements we don't know, they can come in the any order. Okay. At the end, if you count it, so 3 2s has to be there. Yes. And 5 1s has to be there. 1, 2, 3, 4, 5 1s has to be there. And 4 zeros has to be there. Again, see, this order is not important for us. This order is not important for us. At the end, this 2 has to go and 9 swaps will happen. Okay. Second pass. When you see in the second pass also, what will happen? P2. P2. This 2 will go here, right? This 2 will definitely come to the end. Now see this 2. How many elements that are strictly less than 2? Is if they both are equal, why do we do swap? Okay. Now with this 2, if you again see how many elements that are strictly less than 2, simple. 1, 2, 3, 4, 5, 6, 7, 8, 9. See, this is not counted, friends. So 9 more swaps are happened. So already 9 swaps are happened. Then again 9 more swaps are happened. At the end, what will happen, friends? So whatever this 2 will be there will be coming out here. So this 2 and this will be 2, and the remaining elements will be any order. So 2 followed by 4 1s has to be there. No, total 5 1s has to be there. I think 5 1s. And the remaining has to be zeros. I think 4 zeros has to be there. Okay. Next, P3, what will happen? This 2 also will be coming at here, because so that total 2 will be present here. How many swaps will happen? Similarly, how many elements which are less than 2? Obviously 9 more elements will be there which are less than 2. Correct, na? So then what will happen? Finally, this 2 also. Okay, I think 2 also came, and remaining 4 1s will be there. 5 1s will be here somewhere like this, and remaining will be 4 zeros. Okay. Next pass, P4. This one will come and at the here, right, before 2. So 1 will be coming here, and remaining all will be 2 zeros. If this one has to come here, means how many swaps will happen? Simple. How many elements that are less than 1? Strictly less than 1. So with this one, total 4 zeros are there. So 4 swaps will happen. Similarly, with this one also, these 4 swaps will happen. Obviously, with this one also, 4 more swaps will happen. And with this one also, 4 more swaps will happen, because these will create out of order, not in proper order. This will also create 4 more swaps. Yes. At the end, what will happen? All these 5 1s will be coming to the end improperly. So 4 5 1s, and anyhow 2 will be present as it is. So I think 3 2s and 5 1s, and remaining will be 4 zeros. 4 zeros. And now tell me, friends, with this 0, if you want to create a swap, then all elements should right side should be strictly less than 0. But no, right? No swap will happen here. So total how many? 3 9s are 27, and 5 4s are 20. So the final 47 swaps will happen. Finally, 47 swaps will happen. I hope you already all got the correct answer. If not, you please correct it. So first question answer is 47. Next, option B. Give the ordering of second question. Give an ordering of elements to the above so that minimum number of swaps to sort an array is maximum. So obviously this input, right? If all elements in the decreasing order, this will give. It's a good question. These are based on the bubble sort. Okay. Now, if you see uses of this bubble sort, actually this I have taken from the Wikipedia, friends. Wikipedia bubble sort in the use section. If you see, actually this bubble sort is not having much of practical uses. You can just to go through this section. Okay, bubble sort also interacts poorly with the modern CPU hardware, and it produces at least twice as many writes as insertion sort. We haven't seen insertion sort yet. We will talk now. Once if I done with insertion sort, then you can relate which is best among insertion and bubble. You will come to know that insertion is best. So generally, this just for the sake of knowing only, we are knowing bubble sort, friends. Or else it's not having much of practical uses. Okay, right. Next. Second topic that we are going to talk is selection sort. Okay, yeah. If you want, you can take a little pause and have some water, and you can continue. Second one, we'll talk about the selection sort, friends. Again, this is one of the simplest idea that I ever had in selection sort. So this is input and output. Let me show the idea, friends. See here, the idea. So selection sort works by repeatedly. See the word repeatedly. Selecting smallest or largest element from the unsorted region of the array and moving it to the sorted region of the array. So I know you are not getting anything. Let me explain what is sorted and what is unsorted region and all this stuff. The most important thing you need to remember here is selecting the smallest or largest element from the unsorted region. What is meant to be initially given array will be unsorted, right? If it is already sorted, why will apply any sorting algorithm? Correct? Okay. Yeah. So this is the input. Okay. Which they see throughout the discussion, I'll let me take the same input only. Okay. So very simple idea. This selection sort. Select either minimum or maximum. Selecting the largest or smallest. So let me take the smallest. Okay. I will take this element first. Again, this also you can think of multiple passes, friends. So first pass, what will happen is in the P1. Okay. So 0th element we are going to take. See this carefully. 0th element we will take. Including that element, see where you are getting the minimum element in the complete array. At which index you will be getting the minimum element in the entire array, including that element. Okay, when I is equal to 0, so where at what index you find out that minimum element? Tell me here, friends. Including this 9, okay, in the remaining complete array, where did you find the smallest element? Obviously at index number 5. At index number 5, you find out the smallest element. Now what you need to do, you have to swap these two. Swap contents of these two. So which means 1 will be coming here and 9 will be going here. 9 will be going. And the remaining elements will present as it is. So 7, 6, 4, 2. Okay, now? So with this left side, one element came to in its correct position. That is small, because in the final sorted array also, smallest element will come to in its correct position. Yes. Okay. Now you need to continue the story from here in the next pass. In the next pass, you have to continue story from the remaining. So which means in the P2, so I is equal to 1. Now don't disturb the value that is present at I is equal to 0 because it is fine. It is came to in its proper position. Now, when I is equal to 1, you need to find out where did you the next smallest element that is present. Maybe it can present at I is equal to 1 also. No problem. Okay, na? So where did you got the next minimum element? At what index? See here at index number 4. Okay. So now you have to swap these two. So if you swap these two, what will happen? So just for the understanding, let me create a new array. You need to swap index number 1 value and index number 4 value, which means these 7, 2 you need to swap. So these 7, 2 you need to swap. So what will happen, friends? So 2 will be coming here, 2 will be coming, and 7 will be going. So finally, if you see, first two elements happily came to their correct position. Correct? Because these two final came. Now you need to continue the story from I is equal to 2 onwards. Okay, you have to continue the story from I is equal to 2 onwards, which means next time when I is equal to 2, okay, where did you got that next minimum element? At what index? Maybe 2 also can be there. Including 6, where did you find the next smallest element? Yes, you found out at index number 3. So you need to swap these two, which means 4 will be coming and 6 will be going there. So let me create a new slide. Okay. Okay, so you need to swap what, friends? Index number 2 and index number 3. If you swap these two, what will happen? So 4 comma. So if you swap these two, so this will be 4 and this will be 6. This will be 6. So happily, first 3, because 3 passes were over. This is P1, this is P2, and this is P3. First 3 passes are done. Then happily 3 elements came to their proper position. Now remaining, we need to check for remaining passes also. That is P4. P4 also we need to check, which means at a P4, I value is at index number 3. When I is equal to at index number 3, now again including that, where did the next smallest is present? So you have to continue the story on the remaining elements. Okay. I is equal to 3. Next, where did you got the minimum? Maybe sometimes index number 3 or after that, but don't disturb the first 3 elements because they are happily sitting in their correct positions. So, okay, please don't disturb these two. Continue the story from the next index onwards. Earlier I is equal to 2. Now start from the I is equal to 3. Minimum where? Okay, here is minimum 3 only. Okay, when 3, index number 3, okay, where I is pointing, minimum also pointing at index number 3. What is the use of swapping 3 with 3? No use, right? So please better not to swap. So swap when I is not equal to minimum, then you do the swap. When I and minimum both are pointing same, then please don't swap, not required. Okay, now? Next. next pass. Okay, which means in the p5, okay, so the story will start from index number 4. Index number 4 story will start. Okay, again you find out including. Now here you see, friends. Okay, let me maybe create a new array. No confusion. You see here now. First 4, because at the end of the 4 passes, 4 elements happily sitting in its correct position. You continue story on the remaining elements only. Right? So at p5, I is equal to 4. Where did you got that minimum elements? At what index you got it? At 4 only. 4 only, right? When both are pointing same, what is the purpose of swapping? So better not to swap. Okay. Next, is it required from p6? Okay, out of n elements, n minus 1 elements happily coming, friends. Nth minus nth element should compulsory be in its correct position only. So 5 swaps are enough. Okay, so 5 passes are enough. If total n elements are there, then do only n minus 1 times, because only leftover 1 element will compulsory sit in its correct position only. Got it? Very simple idea, friends. And now it's easy to implement the code also. Okay, it's easy to implement the code also. So just to see here. So whatever I have written, maybe I'll take the next slide. Okay. Don't worry, this I will share it for you, friends. See, based on the whatever explained on the left side, I will try to write a code here. So void, okay, void, okay, just a minute. Selection sort, so it will give the input array take, and these 2 parameters it will take as an input. So obviously 2 loops are required. One loop is for traversing all the passes, and another loop is for within the pass. So let me take 2 for loops. One for loop is for int I is equal to 0. So less than n minus 1 is enough, friends. I plus plus. Okay, let me take one variable called as minimum, int min. So initially min also will be pointing to the ith index only. Now j value, okay, which will start from I plus 1. But left side don't disturb them. So j will start from I plus 1, and you can run till this last element j plus plus. Okay, so you just need to compare. You have to find out where you find it the minimum, which means if you find an element, let's say array of j is not array of j is small than existing array of minimum, then what you need to do, friends? So you have to update this min to j. Correct? See, take some time and try to understand what is happening here. So array of j value, okay, if you find that is small than the existing array of min. See, here min corresponding to index, not the value. Min corresponding to index, friends, not the value. So here we are comparing 2 values, not 2 indices. That is why min is equal to j. So which means at the end of the for loop, what happened? Okay, minimum will be now updated by the value where it is the real minimum is available. Okay, for example, if let's say I is equal to minimum, which means I comma minimum both are pointing to same, then please don't swap it. When the swap is required, if I is not equal to minimum, then swap is required. Okay, then you swap it. So I'm writing simply swap of array of I comma array of minimum. It's a very simple algorithm, friends. This is swap it. Okay, this for loop is over. Got it? Very simple idea. This is like once you are done with writing the code, yes, this is already done. Now let's analyze the time and space complexity. Okay, see, earlier I forgot to explain the space of bubble sort. See, space complexity depends upon 2 things, friends. Okay, apart from the given input, what extra space that you are using here, which means this is the given input, this is the given input. Okay, apart from this you should not consider when you're finding out the space complexity. The input things you should not supposed to consider. Okay, extra what else you are using? I am using extra one variable I and an extra variable j. That's it. So if you are using only variables, so temp, those all will come under order of 1 space. Order of 1 space. Whereas if you create an array, then the space will be order of n. I mean, size of the array you need to take it out. Okay, so space is order of 1. Let's come here now. Selection sort. We have already implemented it. Yes. Let's analyze time and space. Okay, first let's see about time. Obviously, friends, so let me talk about first best case and then let me talk about the worst case. First if I talk about the best case input, best case where array is sorted. Okay, so array is sorted. Let me take one sorted array. Maybe this array I'll take. So again, okay, best case input I'll take here, or maybe we'll take these to the next slide and let me explain, because here it will be clumsy. So this selection sort. Okay, the code is here. First, let me take about the best case input. Okay, all elements are in the increasing order. I will take first. That is maybe 10, 20, 30, 40, 50, 60. So this is nothing but a best case input. Now again here the time complexity depends upon what? Comparison along with swapping also, because here comparison is happening and swap also happening. But unlike bubble sort, inside the comparison swap is not happening. Outside the comparison loop, swap is happening. That is the beauty here. Okay, forget about best case and worst case input, friends. How many swaps in worst case can happen? Tell me. It can be anything. Either it is best case or worst case. How many swaps can happen? Worst case. How many swaps can happen at max? At max, because this swap is present outside of this for loop and inside of this for loop, and swaps can happen at max. Let me show now. Okay. First, I is equal to 0. So I is equal to 0. Okay. J value will be starting from I plus 1, which means here. Now, comparisons will happen definitely, because including this, you have to compare these two. Okay, minimum is still this only, which means I is pointing at here and minimum also pointing initially wherever I is there. Okay, now if you find any better element, then that the better element is minimum will point. Better element means element which is less than the array of I. Okay, now is 20 better? No. 30 better? No. 40 better? No. 50 better? No. 60 better? No. So which means comparisons were happened. Let me write here. Comparisons were happened as 5. But swap is happened how many? 0 swap. 5 comparisons are happened and 0 swap. Why? Because I and the minimum both are pointing to same now. Then swap is not required. Okay, next. I value will be pointing at here. Minimum also will initially pointing wherever I is pointing. Now, with the 20, you find is there any better element? No. But comparisons will happen 4 comparisons will happen. But how many swaps? 0 swaps only. 0 swaps. Okay. Next. Comparisons 3. Okay. 0 swaps. Next time 2 comparisons. 0 swaps. Here 1 comparison and 0 swaps. Okay. That's it. So overall, if you see in terms of in general n. Okay. So comparisons are n into n minus 1 by 2. Okay. Whereas swaps are 0 swaps. But still the time complexity will be n into n square, which is order of n square. Okay, at max n square. This n square is coming from comparison, friends, not from the swaps. But still you have to take into consideration. This is when it's a best case input. What if I give the worst case input? So remember, friends, this is for the best case input, BC. Okay, best case input. What if I take the worst case input? In the worst case input also, comparisons will not going to change. Only thing, swaps will change. Like every time swap will happen. But the swaps are n square? No, swaps are n only, because this is present outside of this for loop and inside of this for loop. This for loop will run maximum n minus 1 at max n times, approximately n times. So worst case also, this is order of n square, but this n square is coming from where? So here n into n minus 1 by 2 comparisons plus n swaps only. N and this is n square, which is bigger? N square is bigger. So that's why in the selection sort, friends, okay, best case and worst case, both time will be n square only. Okay. Now, unlike bubble sort, can be further modified, where we can best case can be further modified to or reduced to n. Is it possible? Because in best case we have done, right, by using a flag variable. Now, is it possible here? Try to think. Okay, you can work out, and if no, you can please let me know the answer in the comment section. if it is possible. If it is not possible, then the best case will be n square and worst case is order of x square. Okay, what about space? So this is time. This is time. Okay, what about space? If you see here, friends, apart from the given input, we are using only variables only, nothing else. So space will be order of 1. So order of 1 is the space complexity. Okay, good. So till now done with the bubble sort and selection sort, friends. So in the next slide, we'll talk about now time complexity will done. Now we'll talk about the insertion sort. Okay, yeah. If required, you can take a maybe 1 or 2 minute short break and you can continue. Okay. Yes. So let's continue this insertion sort. Okay. So again, the input will be unsorted array. Now you need to sort this array using insertion sort. So as usual, first we'll see the idea behind the insertion sort and let's continue. Right. So the idea. So insertion sort works similar to the way you sort playing the cards in your hand. I think in our childhood we might have played the cards game, right? Cards. Okay. So pick all the cards in one hand. Okay, one hand try to take all the cards. Okay, you just need to take one outside and you put it in the beginning if they are in the not sorted order, like that. Okay, so the array is virtually, now let's come to the how you have to done programmatically. So the array is virtually split into a sorted and unsorted part. Values from the unsorted parts are picked, okay, and placed at the correct position in the sorted part. Okay, so here array is divided, virtually it is divided, physically it is not divided, friends. Virtually it is being divided in 2 parts. One is unsorted and second is sorted. In the unsorted part, we will pick one element and we will place it in the sorted part. Okay, I haven't understood anything, but let me talk. Yeah. Okay, so this is the array initially that they have given. Now let me explain, friends, what is happening here. So here what we will do is, virtually we will divide array into 2 parts. In the first part, I will take array is sorted. Let me use a different color. So this part, left side part, I'll always assume. This left part, I'll always assume array is sorted. And right part, I'll assume array is not sorted. See, when array is having one element, by default, it is sorted, friends. Okay. Now, let me try to take this element. Now, I have to find out what is the correct place for this 7. Okay. Okay. Assume in your hand, total 6 cards are there. Every card is having some number. Okay, card number 9, card number 7, 6, 4, 2, 1. Now, finally, you need to, at the end, arrange all the cards in an increasing order. So, first, you will be taking one is, let's say, 9, 7, 6, 4, 2, 1. Now, let me take the 7. This is 9, okay, and this is 7. I will take the 7 and I will put it before 9 and I will move this 9. Okay, which means I will take this 7 separately. Maybe I'll call it in a variable key. This I'll call 7. Okay. Now, okay, I will move this 9 here. So if I move, now I'm going to compare this 7 with respect to 9, friends. So this 7. Okay, let's not worry about how I am implementing. First, understand the idea. Once you know the idea, implementation will become very easy. Okay. Left one element I have taken. First, initial array virtually divided into 2 parts. First part containing only one element and that part is sorted. And the second half containing some elements where all these elements are not in sorted order. Now, from the unsorted array, you can pick any element, friends, and put it in its correct position. That's it. Rather than picking whatever the element that I want, let me go it in a proper order, which means I'll take this element 7. One by one I will take. I will take the 7 outside. I will compare with the elements that are present in the sorted part. Okay. Only one element sorted. So 7 and 9. Now you see this key value will be small compared to this 9. So I will move this 9 here, which means I will try to move this 9 here. Okay. And this 9 will anyhow present it here. Okay. Which means this 9 will go here and 9 will present here. Next, with the key, is there any element that is left here? No element, right? So that comparison will be ended. Then finally, this is 7, I will try to place it here. Okay, at the first time you might not understand, friends. Just be with me at the end of the complete array. You will get that idea. So these are 7, 9. Now they are in the proper order. Okay. Next, remaining elements will be 6, 4, 2, 1. 6, 4, 2, 1. Okay. Now see how happening. Now don't disturb the elements which are already sorted array, which are already in the sorted manner. Let's not disturb those. Okay, you take an element. from the unsorted part. Okay, 6. Now try to, now this time every time I will update this value here. So 6 will be 2. Sorry, key will be 6. Now I will compare. Does 6 is small compared to 9? No, na. So movement will happen, which means 9 will be coming here. Okay, 9 movement will happen. So here, simple friends, movements and swaps. Okay, movements and updating, these two things, the insertion sort final time complexity will depend. Okay, this 9 will be moved to here. Then I will again compare 6 comma 7. Does 7 is better compared to 6? No. Then I will move this 7 to here, so which means 7 will be coming here. Okay, now after that nothing to compare, then put this 6 here. Okay, so put this 6 here, which means what you will get it here, 6, this will be 6, and this will be 7, and this will be 9. So this is done. Now left side, all these elements are in sorted. Now these are in not sorted. So 4, that is 2, and that is 1. Now next to take this element 4, which you can store it inside that key. Now you compare. This is all these elements you need to compare one by one. Okay, all these elements you need to compare one by one. Right now, partially I'll write the code here. Void insertion sort on the input array. Okay. Now see here, friends, I am starting always from the index. Always I'm starting from from the unsorted part, right? So first element, let's not worry. Start from the here. I is equal to 1. So here, okay, something like I is equal to 1. Okay. So while, now see here, for the I is equal to 1, and I'll go till the last I plus plus. Okay. Now see here, let me take one variable called as key, and inside key I will try to store the array of I. So here also, if you see, you are starting from here, right? This we have already stored it in a key. Now I will take one more variable called as j. I will take one more variable called as j. Okay. This I'll start from the I minus 1, which means left part. Okay. If in this example you say, if I is presented here, okay, j value, now I will be starting from here, and this j value go till the end. Since j value that you are starting from I minus 1, so j value that you are starting from I minus 1, okay, j is equal to I minus 1. You have to make sure j value, every time you are decrementing one by one, comparing with its left side, there might be a case when j becomes 0. So you should be very careful. J should not go into the negative part. So while j is greater than or equal to 0 and j is greater than or equal to 0, and what you have to compare, friends, if you found, let's say, key value, whatever the key that you are comparing is small compared to array of j, compared to key value is compared to array of j if it is small now. So what we are going to do is, array of j plus 1 is equal to array of j. See, this is movement. Okay. Let's see what will happen now here. You take this example. Here only you try to take. Okay. I can start from the beginning. Friends. I is equal to 1, which means I value I will be starting from here initially. I value present it here. J value always pointing one element to its left side. Okay. So key is equal to, I have taken array of I. So here key is equal to, what is array of I, which is 7. Now I have to place 7 in its correct position. Now our assumption is, we have divided array into 2 equal parts. One will be its left side is always sorted. One will be its right side, that is unsorted. So from the unsorted, pick one element, place it in its correct position. That is the idea. Okay. Now 7 I will start comparing with one by one 2 elements that are present on the left side, which are actually sorted. Okay. Now 7, if I compared with 9, obviously 7 is small, right? Compared to 9. Yes. I found a key which is small compared to array of j. Then what I have done, array of j plus 1 is equal to array of j, which means j plus 1 is equal to array of j, which is 9 will be coming here and 9 will be present here also. Okay. And the remaining elements as it is. So don't disturb them. 6, 4, 2, 1. Okay. Now, if you are not taking key separately, then what can happen? This 9 might be lost. Correct? Okay. Next, decrement the j value. Next, decrement the j value. Now, when you see j becomes 0, right? No, j becomes -1, right? Then this loop will be failed. This loop will fail. When j is pointing to negative, which means -1, let me increment the j value and I'll try to place key here. I will try to place key value, which is here. Array of j plus 1 is equal to key. Now you might be getting the doubt here. That is, this loop might fail because of two conditions. One condition is j might be pointing to the negative index, or key might be greater compared to array of j. Because of any one of these conditions, this loop might fail. Does it mean that any one condition, if loop fails, you have to write this condition? Yes. Be with me, you will understand now. Okay. So at the end, so here key value will be updated. That is 7, 9. 7, 9, friends. Now you have to start the loop from the I is equal to 2 because I plus plus. Okay, I. Now here, what is the key value? So key I will be taking 6, which means key is equal to 6. Okay, na? Compare. J value will be I minus 1. Okay. Now check this. Now I am comparing. Whatever that key value, is it small? See, why I am checking small? If it is small, so that I will put before this 9, right? Before this 7, right? So that 6, 7, 9, they are in the complete order. Ultimately, you need to put all these elements in the sorted order. That is why I am checking. If this is small, so this should not, the actual elements should supposed to present, right? So move this 9 here. Okay. Let me move this 9. Then decrement the j value. Decrement the j value. Now 7. Does this 7 is small compared to 6? No. 6 actually key itself is small. So this 7 should not present. So just to move them. Move to in its right side. So this j plus 1 will become j, which means 7 will be coming. Then j value will be decremented. So j value will become 0. Then j value will become -1. Then what will happen? So j plus 1 is equal to key we are keeping at the end, which means so this will be 6. And this will be 7 and this will be 9 and the remaining elements as it is, that is 4, 2, okay. So the next time you should start from where I value I plus plus, which means you have to start I is equal to here. I is equal to here. Again, now the key value will be 4. Now you have to compare, friends. Now you have to compare 4 with all these elements that are present on the left side. First you compare with 9. Now if you see 4 is small, right, compared to 9, which means 9 should not supposed to present. So move this 9 here. See, why I am moving like this? Because 6, 7, 9, if you move, there is an empty space will be 4. So that finally what will happen? So finally what will happen? 4 will come here and all these 6, 7, 9 will be moved like this. Then the next time you can start I value from the index number 4. That is the idea. Okay, so when you start this, these 2, 1 will be like this. That is the idea. So in the next iteration, what will happen? The key value will become 2. When again key value will become 2, what will happen? So this 9 will be moved here, 7 will be moved here, 6 will be moved here, 4 will be moved here, then 2 will be placed here. So which means in the next iteration, what is going to happen here? Next iteration, this 9 will be moved here. But still 9 will be present here. Next time when 7 is overwritten with 9, then 7 will be coming here. Then 6 will be coming here. Then 4 will be coming here. 4 also will present. Just it will go. But still that element will 4. But that 4 will be overwritten by this condition. Array of j plus 1 is k. So which means now currently key is 2, right? So 2 will be modified. Next 1 will be present as it is. The next time what's going to happen? Now if you see I value, that will be presented here and j value will be starting from here till all its left side. Now all these many comparisons will happen. Okay. Now you found out that this time key value will be 1, right? So this time key value will be 1. Now basically you are inserting 1 in its correct position. At the end, that is what happening, friends. Okay. Now this 9 will be moved here. Okay. 7 will be moved. Then 6 will be moved here. Then 4 will be moved. 2 will be here. And then finally 1 will be here. So array is finally sorted. Are you getting the, friends? So you need to put this value in its correct position. That's right. Okay. But initial assumption is always left side part will be sorted and right side is always unsorted. Pick element from the unsorted, put in its correct position in the sorted order. After keeping, again the left side part should become sorted. That is, if you see anytime, if you see left side anytime, if you see, it is always in the sorted order. Okay. So here now the time complexity depends upon two things, friends. Two things. One is movements or shifting, whatever you can call, and then comparison. Here the time complexity depends upon comparisons. Okay. Plus movements. Movements. Correct. Movements are some people also called as shiftings. Shiftings. Okay. Right. Now, okay. Again, when the analysis of time complexity comes now, two types of inputs we need to consider. That is worst case input and the best case input. So let me take one best case input. Okay. Okay, let me take the best case input first. So all the elements I'll take it in the increasing order. 10, 20, 30, 40, and 60. Okay, let's analyze, friends. So I'll even put the code also so that it is easy to see. Okay. So how many comparisons are happening and how many shiftings or movements are happening, we have to see now. So first time, if you take key is equal to 20, so let me write it here. When I is equal to 1, see, friends, now key is equal to array of I. Okay, yes, key is equal to route 20. Now you compare that. Does 20 is small compared to 10? Tell me here. Does 20 is small compared to 20? No, comparison is not happening. One comparison happened, but that is failed. So here let me write comparisons and let me write movement. Yes, one comparison is happening, but no movement is happening. 0. Okay. Next, I value will becomes 2. When I value will becomes 2. Okay. When I value will becomes 2, which means I will be currently presented here. Now see. So we are comparing first again. See this loop. Okay. Does key is small? Key is 30. Does 30 is small compared to 20? No. Okay. Only one comparison is happened here. Okay. But when this loop is failed, the control will not go inside. If this is true, then only loop will go inside, right? Okay, when this condition failed, then while loop will not get executed. See, why we are comparing only 30 with 20? Why can't other elements we are ignoring? Because we know that if this 20 is small than 30, then definitely 20 left side all elements are in less than 20. Therefore, if you know 20 is smaller than 30, then definitely 100% sure left side will be smaller than 20 only, which is ultimately less than 30. Correct, na? That is the beauty here. So assumption is not the assumption is always happening, friends. That is, left side will be sorted, right side unsorted. So only one comparisons and 0 movements. Next, when I value becomes 3. Okay, when I value becomes 3, which means I is at here. Key value is 40. 40 is compared with 30, and this while loop will fail, and 100% sure remaining elements will be small. Okay, so only one comparisons and 0 movements. So next, I is equal to 4, also same reason. Okay, only one comparisons and 0 movements. When I is equal to becomes 5, only one comparisons and 0 movements. When I is equal to 6, loop will fail. So overall, if n elements are there, n minus 1 comparisons are happened on the worst case. Therefore, the best case time complexity will be depends only on the comparisons and no movements. So n minus 1, in general, it is order of n. This is when, friends, best case. But we have to take worst case also. Correct. Let me duplicate this slide and we'll talk about the worst case. Worst case, this will be changing. let me talk about the worst case. Worst case time complexity. So this time I'll take all elements in the decreasing order: 60, 50, 40, 30, 20, and the 10. So number of elements are equal to 6. So as usual, friends, so I is equal to at index number 1. Now we have to see how many comparisons and how many movements. So in short, I am writing COMPS, comparisons and number of movements. Okay. First I is equal to 1. So this time key is equal to 50, right? Because when I is at here, so key is equal to 50. Correct? Now this 50 is being compared with 60. And now we check 50, 60 true, right? So one comparison is happening. So clearly if you see 60 is small, so definitely here movement will be required. Correct? So movement will be required. Then 60 will be coming here. So one movement is happened so far. And next time j becomes 0, loop will fail. And okay, so here 50, 60 will goes here, then 50 will be coming here. So finally here. So 50 will be coming here and then 60 will be here. That is what will happen at the end of the first iteration. So next time I value will becomes to I is equal to 2. So which means now I value will be coming here. Now again, you need to take 40, key is equal to 40. Now 40 you have to compare with all these elements. 40 you have to compare with all these elements. Now you check here, friends, this is 40. Okay. And you want to check with these two elements. Obviously these two elements you need to check. 60 with 40 you need to check. Then after that 50 with 40 also you need to check. Okay. You need to check. Okay, just to take pause here, I'll explain one other concept and I'll come to here, friends. See, that other concept is, you want to understand, like you need to understand one term called as inversion, friends. So let me explain what is meant by this inversion. So this inversion is actually a pair which contain two elements. So I comma j, for all I comma j, where I comma j are from 0 to n minus 1, which is basically they are two indices out of all n elements. So I comma j are pointing to two indices, that is 0 to n minus 1. Anywhere they can point. First condition, they should be different. I comma j should be different. Second condition is I should be less than j and array of I is greater compared to array of j. Then array of I and array of j is called as an inversion. Okay, with this I, j, array of I, array of j, you might not understand. Let me take an example and I'll make this clear. If you take this element, so the condition should be I less than j, which means I is always smaller, and array of I or array of I is bigger compared to array of j. Array of j. In these two, I should be not equal to j. That is important. I should not equal to j. Okay. Now, which means simple. You take this I with 0. When I is at index number 0, these all elements which are present to its right side, because if you take 0, 0 less than 1, 0 less than 2, 0 less than 3, 0 less than 4, 0 less than 5. Now all possibilities to make a inversion. See, I is 0. If see how many elements that are less than 9. Yes, we have a 7. So 9 comma 7 is an inversion, because you see this condition is satisfied. Na? I should be less than j index and array of I should be greater compared to 7. Then 9 comma 6 is an inversion. Then 9 comma 4 is an inversion. Then 9 comma 2 is an inversion. Then 9 comma 1 is an inversion. These are all inversions that are possible with 9. Next, when I becomes here with the 7, how many inversions? With the 7, this 9 will never become an inversion, because I should be always less than j. With the 7, how many inversions are possible? With 7, 6 is an inversion. Because left side, right side 7, all are small only. 7 comma 4, then 7 comma 2, then 7 comma 1. Similarly, when I is at 6, index number 2, these elements will now never form an inversion, because I should always less than j. Now with the 6 comma 4 is an inversion, 6 comma 2 is an inversion, 6 comma 1 is an inversion. Next, when I is at 3, 4 to 4, 1 are inversions. 4 comma 2, 4 comma 1 are inversions. Next, when I is at 4, When I is at 4, this will never become an inversion, friends, because I should always less than j. 2 comma 1 is an inversion. 2 comma 1 is an inversion, right? So total, these many inversions are possible. So if n elements are there, so here 5 inversions, here 4 inversions, here 3 inversions, here 2 inversions, here 1 inversion. So overall 5 plus 4 plus 3 plus 2 plus 1. In general, n into n minus 1 by 2. So maximum inversions that are possible. This is the max. So max inversions possible are n into n minus 1 by 2. Okay, na? N into n minus 1 by 2. So which is order of n square. Right? What about minimum? If all arrays are sorted, friends, if all elements are sorted, then no chance of any inversion. So minimum inversion possible are 0. So this is the concept of inversion. So minimum inversions and maximum inversions. Okay. Now let's go back to the previous case, that is analysis of the insertion sort time complexity. Okay, now we are at here I is equal to 2. Now 40, we are comparing with 60, then small, we have to, movement is required. This I, again we need to compare with this, then movement is required. So when I is equal to 2, 2 comparisons under 2 movements. 2 comparisons under 2 movements. Correct? Okay. When I is equal to 3, movements depends on number of inversion pairs, friends. Simple. Okay. So at the end of the by the time 2 iterations are over, how it looks like? It is looks something like 40. Okay. Then 50 and then 60. Okay. Okay. At the third iteration, right? I is pointing at here. Now you compare this 30. See, all these 3 will form an inversion because 60-30 inversion, 50-30 inversion, 40-30 is an inversion. But comparisons are, yes, again 3 comparisons, then 3 movements will be required. So like that, if you goes, n into n minus 1 by 2 comparisons are there. And how many inversions are there? Worst case, these many movements are required. Movements are shifting, whatever. Okay. So this, so n square, n square. So the worst case time complexity will be order of n square. Order of n square. Okay. So worst case, the time complexity of the insertion sort is order of n square. Now people often they'll represent like this, friends. So whether it is best case or the worst case is important here. So in the best case, if you see, best case, see the comparisons and the movements. N comparisons are there, I mean, in terms of big O, and 0 movements. Okay. What about worst case? What about worst case? Comparisons are n square. I mean, I'll write in terms of big O. Okay. This you can write the order of 1 plus, so which is eventually leads to order of n. Comparisons also order of n square, worst case, plus order of n square, which is essentially leads to order of n square. Okay. Now, among these two, what is the minimum in comparisons among these two? Minimum n comparisons are required. Whether it is best case or worst case, minimum n, worst case if it is n square. Right? So n plus, so n is compulsory. Okay. Then depends on inversion. If inversions are 0, then it is order of n. If inversions are the behave worst case, then order of d, order of n square. So order of n plus d is the time complexity. So here d actually represent number of inversions. Number of inversions. If it is the best case, 2 things, friends. If it is the best case, okay, 0 inversions are there, which is order of n. And if it is the worst case, okay, n square inversions, order of n square. Square. This you can think of order of 1. So therefore, what is the best case time complexity? N plus 1, that is order of n. What is the worst case time complexity? N plus n square, which is n square. So order of n square. That is how they'll represent, they'll write it. Okay. So this is the idea of the insertion sort. Right? Okay. Code is already present. Yes. Okay. So if array is almost sorted, then people will prefer this insertion sort, right? Because why? In that case, okay, less number of inversions will be there. If array is almost sorted, which means let's say 3/4 region are sorted, or 70-80% of array is sorted, then compared to bubble and selection, this will work better, friends. Insertion. Okay, so yeah, that's it, friends, for this class. I think it will be enough. Remaining sorting algorithms I'll take it in the next class. Okay, otherwise this video will become lengthy. This I'll take it in the next class, and we have some more things also will be coming up in the future. So that's it for this class. Yeah, so thank you for attending. Okay, so I hope you understood all the sorting algorithms well. Now again, you please go through these algorithms, right, and you implement it on your own. Please don't look at the code, understand the idea, take pen and paper and implement it on it in your own, so that you remember for the longer amount of time. Okay.